So, good afternoon and welcome to the ESAB Specialty Alloys live event. My name is Clemente Talarico, and with me as the presenter we have Mr. Peter Stones and Mr. Per-Åke Björnstedt as well for technical support. I'm pleased to announce here the second presentation of the new presentation program of ESAB Specialty Alloys, which will happen every third Friday of the month at 14:30 European time via Teams live event. The second presentation of the program will be the one starting in few seconds with the title, "Why are these duplex grades so good?" We will be very happy to answer your questions at the end of the presentation, which you can type in the Q&A box you will find in the top right of your screen. We intend to present on about 30 minutes and take 10 to 15 minutes more for answering your questions. So, and now let us start the show with Peter presenting. Enjoy!
Thank you, Clemente, and welcome everyone. Thank you very much for joining us again. This is the second in the series. We intend to do one every month, and the topic of this one is, why are these duplex stainless steel so good? So as Clemente mentioned, please use the Q&A box to ask questions, and we'll do our best to answer as many as we can at the end after about 30 minutes. Excuse me. And there will be our contact details at the end of the presentation. Please take note of the emails and numbers and feel free to contact us at any stage. So, what I want to discuss in this presentation, the topics I want to cover are the characteristics about duplex stainless steels. So what are the properties that they have that make them so good, and why, what applications do we make benefit those properties? It's interesting to go into the history of the development of duplex stainless steels and where we're up to right now. This thing called hyperduplex, what is it? The PRE number is very important with respect to certainly stainless steels and duplexes, the duplex family. So what is the PRE number and how does it relate to the suitability for corrosion resistance? And then it wouldn't be an ESAB presentation without advice and tips on welding. So we're talking specifically welding the duplex family, why the parameters are so important. So the word duplex originates from the Latin meaning twofold. So this is a mixture. The duplex microstructure, if you looked under a microscope, is a mixture of these two phases of steel, austenite and ferrite. The term austenitic stainless steel, for example, such as a 304L, a 316L grade that you may be familiar with, they're called austenitics, but they're not 100% austenitics. They'll still contain up to 15% ferrite, but they're known as austenitic stainless steels. There are something else called super austenitics, which is another thing entirely. However, for a duplex stainless steel family, we're talking in the region of a 50-50 mixture of austenite and ferrite. These things weren't available until the 1930s. Harry Brearley from Sheffield invented stainless steel. He found out how to add chrome and how to generate this two-phase or this austenitic ferritic material just before the First World War. And so it took until the 30s until the duplexes were developed from the first developments of stainless steel. The advantages of duplexes and why people use duplexes is basically their attractive mechanical properties. They're very much higher yield strengths than an austenitic stainless steel, for example. However, it's corrosion resistance that they score. Pitting corrosion, stress corrosion, intergranular corrosion are all areas that receive so much attention. Corrosion is such a complex subject, and it's going to be the subject of a presentation all on its own in the future. So the benefits associated with corrosion resistance and mechanical strength lend themselves perfectly to the applications that the Duplex is used for. So to look under a microscope, you see this structure. The light areas are austenite, and austenite is described as a face-centered cubic. So the molecular structure of the austenite is a face-centered cubic. You can see there are molecules basically in every gap, whereas the ferrite are the black lines. This is what's known as a body-centered cubic. So you can see the austenite has an extra molecule in every space. Okay, so that's why the property is different. So what we're trying to achieve in the Duplex is a 50-50 split between the austenite and ferrite. It doesn't necessarily mean that all the families of Duplex have to have exactly the same amount of chromium, the same amount of nickel. You can see typically chromium is between 18 and 25%, nickel between 4 and 9, and then anything up to 4% of molybdenum. And what do the various alloying elements add to the properties of these steels? Duplexes are difficult to produce. They are more difficult to produce than a standard ferritic or a standard austenitic stainless steel, and it's because you're trying to manufacture this 50-50 split between austenite and ferrite. Chromium in there is what makes a stainless steel stainless. Yeah, anything above 12% chromium generates a chrome oxide layer on the surface. Chrome oxide is very, very resistant to corrosion. Okay, but what chrome also does is it stabilizes the ferrite. Okay, in order to get a good balance between the ferrite and the austenite, then obviously the content of chrome has got to be balanced with the nickel. Nickel wants to create austenite. Molybdenum is to increase the passivity and chemical resistance. That's why molybdenum is used. It's very good at increasing the resistance to corrosion, from pitting corrosion. Okay. High concentrations of molybdenum, it wants to create these harmful intermetallic compounds, and I'll show you that, illustrate that a bit more later on. Nickel's a very strong austenitizer. Okay, it wants to create austenite out of the ferrite. That's what it does. When the alloy is liquid in a molten phase, it's ferritic. As it's cooling down, you have nickel in there, and the nickel will cause the austenite to form. Okay, obviously you can have too much in there. You can get the balance wrong between ferrite and austenite, so that's where you need to be careful. Nitrogen in there, it's also a strong austenite former, and it's cheaper than nickel, if you can imagine. So the manufacturers like to put nickel into the Duplex grades in order to create the austenite. Obviously, again, you can have too much nitrogen, you get too much austenite. Manganese is good for getting rid of impurities, as with any steel. So small amounts of oxygen and sulfur within their impurities, that manganese will eliminate the effect of those. And also some manufacturers use tungsten up to 2% to improve the corrosion resistance. The addition of tungsten does make a less stable alloy than those without. So there are grades of super duplexes that use tungsten, and there are grades that are also super duplexes, but they have no tungsten in them. Looking at the history, this is quite an illustrative graph here. Along the x-axis is the timeline, the years. So the first generation of Duplex stainless steels in this range called Duplex were around about the 40s and 50s. Okay. Incidentally, the grades that are listed in light blue are the ones that were specifically invented by Sandvik. These were developed by Sandvik. Okay. Up the y-axis is this thing called the PRE, the pitting resistance equivalent number. So this is the equation for it. It's got no units, it just comes out with a number, and it's an addition of the percentage of chrome, molybdenum, and nitrogen within the alloy. Add that up, and you come out with a number. Okay, so the definition of the duplex family is made by using the PRE number. We have this thing called a lean duplex, which has a PRE number up to around about 28. Okay, the definition of a duplex grade, the PRE number is anything up to anything over 32, something like that. The super duplex is above 40, and then very uniquely in the Sandvik ESAB Exciton range, we have this grade called hyperduplex. Okay, so this has a PRE number above 48. Okay, so it means that the resistance to pitting is much higher the higher that you go up the scale. Okay, incidentally, the discrimination between first generation and second generation is the first generation were not weldable. Okay, so these grades were produced in the mills, but you couldn't actually weld them. It wasn't possible to get a proper structure with welding. Whereas the second generation, they're all weldable. And yeah, that's what we're talking about. We want to talk about welding. So on the scale, if you want to see where something that you may be more familiar with, like a 316 austenitic stainless steel, on the PRE scale, using this formula again, the resistance to pitting from 316, we're talking a number 24. Okay, whereas a standard duplex 2205 stainless steel is 32. Okay, and again, we talk super duplex and hyper duplex. And what does that have? What effect does that have? So a standard corrosion test for stainless steels, for all the families of stainless steels, is a G48 corrosion test. So this, all of these samples from the various alloys have been submersed in this 6% ferric chloride solution, but at 80 degrees. So this is it's a nasty corrosive solution, and you can see the effect. I don't know the amount of time, but they've all been in there for the same amount of time. Okay, and the effect on the 316, which has a PRE of 24, you can see the whole surface has been decayed. So this has suffered lots of corrosion, and you can see these areas where pits have started to form. So the corrosion's broken through the surface. And pitting corrosion is a bit like an iceberg. The damage is all underneath the surface. So this is in a very bad way. Compare that with, say, a lean duplex. You can see there's been some effect there. There's a lot of pits. The whole surface is discolored. Standard duplex is a little bit less. This is super duplex. Okay, 2507 super duplex. So it's been in the same amount of time as all of these, and it looks to the eye to be barely touched. Okay, so that illustrates the difference between a PRE of 24, a PRE of 42. In terms of mechanical strength, again, this is a fairly simple illustration. The 316 is a yield strength around about 200 megapascals. The lean duplex is 400, twice as good, fantastic. Okay. I'm sorry, what I didn't mention before with lean duplexes is that they were really invented at a time when the nickel price was really, really high because they use less nickel. So they're obviously cheaper. Sorry, yeah, and for less cost, if you like, of producing a lean duplex, you've got twice the mechanical strength. The duplex is around about 460, super duplex up to 550. And then this thing, a hyper duplex, 27 chrome hyper duplex, has a yield strength way above 670. Okay, so you can see there's a step change in the development. Lean duplex to duplex, duplex to super duplex, and then super duplex to hyper duplex. So you've got properties that are fantastic at corrosion resistance, specifically pitting corrosion, intergranular corrosion. And you've got fantastic mechanical strength. Okay, that's why these things are so good. In terms of weldability, we always want to talk about welding. In a previous presentation, I mentioned the thermal expansion of stainless steels. So a 316 stainless steel has got twice the thermal expansion almost than a carbon steel. So for a welder that's not familiar with welding stainless steel, this is an issue. This is a problem that has to be addressed. It has to be addressed in the design and the fixtures, the way that you weld it. It has to be addressed. It's a problem for the first time. Obviously, it's easy to overcome, but it has to be known. If you look at the duplex steel family, it's only just slightly more than carbon steel. So in that respect, it's easier to weld. The hyperduplex, the thermal expansion, is just about the same as carbon steel. Okay, so even though you've got all these alloys going on, you've got 27% chrome in this one, for example. In terms of thermal expansion, it's a lot less than austenitic grades, and it's around about the same as carbon steel. So in that respect, it's easy to weld. Okay, so how is duplex made? Going back to a transformation diagram, what we're trying to do, what the manufacturers in the steel mills are trying to do, is basically to cool this nickel, chrome, iron mixture down in the middle section where you've got a nice balance of austenite and ferrite. And what that means under the microscope, if you see here, this is the base metal. It's a fantastic cross section. This is the base metal. You've got nice fine grains. We're going to the heat affected zone, and then the weld. The weld, you've still got a very nice mixture of, it looks to be a good proportion, 50-50 austenite ferrite, but the grains are bigger. Okay, so this has been made molten and it's resolidified. However, it's been done very well, and you've still got a nice mixture. It's still a duplex structure. Okay, so in terms of welding these alloys, we'll talk specifically about joint preparation, shielding gases, heat input, and the effects of getting it wrong. Okay, usual stuff. Exactly what we talk about with all kinds of welding. Okay, joint preparation, with the more higher the alloys, then, to put it in layman's terms, the stickier, the more like chewing gum that the weld pool becomes. So in order to compensate for that, you need to design the joint to be wider. The joint gaps need to be wider to enable this poor fluidity of the weld pool, to enable it to flow into the joints. Okay, if you don't, then you're going to get lack of fusion areas. In summary, shielding gas, I don't want to particularly read this out. Obviously, there were recommendations for shielding gas. One of the most important things with duplexers and TIG welding, because of the high intense heat of tungsten welding, is the addition of nitrogen. As we said, nitrogen promotes austenite. It's very fast moving, and nitrogen in the weld gives more time for the ferrite to turn to austenite. Okay, in TIG welding, then nitrogen will be burnt off and needs to be compensated, and this is why. So these two photographs illustrate, on the left hand side we have no nitrogen. So this has been welded with no nitrogen. So you can see in the fusion line we've got very big areas of ferrite. Okay, these dark areas are ferrite, basically pure ferrite. So this means that you don't have a duplex structure. So in these areas, you don't have the corrosion resistance and you don't have the mechanical strength. If you compare that to, say, 5% nitrogen, typically we'd recommend 3, but this was for in a laboratory. So the addition of nitrogen has basically converted the ferrite to austenite. You've got a lovely duplex mixture all the way to the surface. In terms of purging gas, basically the same again. We would recommend 100% nitrogen, or certainly 90-10 hydrogen. In the bottom of the weld here, you can see again it's a fully ferritic area, so there's no strength, there's no corrosion resistance in the bottom of the weld. That's why we recommend using nitrogen in there. Okay, nitrogen will convert the ferrite into austenite to give you a good duplex mixture. Okay. In terms of heat input, you can see basically we'd recommend as low as possible, even down to 0.2 kilojoules, which is really, really low. Obviously, you still need to weld, you still need to get fusion, but keep the heat as low as you dare. So obviously, the more highly alloyed, so we're getting more highly alloyed from lean to duplex to super to hyper, basically the less heat that we recommend putting in there. And really, this is why. Okay, so the going back to school, your time transformation diagrams, this is illustrating the areas where from being in liquid phase, in a liquid form, as you're cooling down, as you get dwell times within these noses, okay, then that's when these things are produced. Okay, so the intermetallics are produced, this nasty thing called sigma phase, for example. If you get dwell times within these temperatures, then that's when the intermetallics will be produced. The addition of chrome, moly, tungsten, silicon, that pushes this nose further out. So that's why, say, on the same scale, lean duplex would be here, super duplex, and the hyper duplex. You're basically giving yourself less time to transform, to cool down without spending any dwell time within these regions. Okay. If you're following this curve as a cooling rate, then that's too slow. Okay. Presence of these phases of the sigma phase, the chi phase, they're like little pockets of weakness within the microstructure. So you can have what looks on the surface to be a nice duplex microstructure. However, there will be intermetallics within there, and you'll see that I've got an illustration of that on this slide here. So this has taken too long to cool, and you've got these dots of intermetallics, little pockets of weakness. So these are areas within the structure that are weaker than the surrounding areas. They don't have the mechanical strength. They don't have the corrosion resistance. So too many of those, and the structure is no good. Okay. How do you get too slow cooling? It means it's got too hot, too high heat input, or too high interpass. The welder couldn't wait. He couldn't wait for the interpass to go down below the recommendations, below the 150 or the 100. He wanted to get another pass in before he went home. There's too much heat in there, so it's slowing down too slowly. You're going to be within these areas where you're going to generate the intermetallics. Similarly, again, the welder wants to go home. He wants to get another pass in, another couple of passes in. He doesn't want to go over on the interpass temperature, so he quenches with water, say, or air blasts. If you're going to be cooling too rapidly, then massive grain structure and chromium nitrides, which is equally as bad. What we're trying to achieve is a nice middle of the road and maintaining this nice duplex structure. We've got a little troubleshooting chart there for what's happening if you're getting sigma phase, heat input, heat treatment. I don't want to read it out, and the presentation is available to anybody that requests it. But there are things in there, little tricks about using nitrogen, the corrosion test. We've got some nice tips and tricks for passing the G48 corrosion test. So to close off, really, the last thing I want to talk about are applications of these duplex grades. Transport is a good example of the use of duplexes these days. Because of the mechanical strength of them, then you can reduce the thickness. You reduce the thickness, you reduce the weight. Everything's about weight when we're talking about transport. So oil tankers, rail carriages, for example, are two excellent examples that are in production now, right now. Obviously, offshore, we're talking high corrosion, offshore applications. There's a very nice example of submerged arc. You can submerged arc these duplexes, that's not a problem. And we've got another example here with a flange, which has been done by Orbital TIG. So again, the application is for offshore. So they're using duplexes or super duplexes even in some of the more corrosive environments for the pipe work. This is a nice application that we had in Singapore in an oil refinery, whereby the conditions, the working conditions, were at 125 degrees, but it had 13% chlorides. So in terms of corrosivity, it's a nasty corrosive solution, and it's at temperature. So initially, the designers were thinking that they'd have to use something like an ink alloy, a 625, use a nickel alloy, which is obviously going to be hilariously expensive. So the solution was found to be, by trials and testing, was found to be by using hyperduplex. So this hyperduplex available in tubes, we use for the heat exchanger tubes. The tube plate was a clad plate with super duplex and then hyperduplex, and then everything was welded together with hyperduplex. So please, I'm not trying to suggest that the hyperduplex is a replacement for alloy 625, but in this application where the corrosion was from chlorides, chlorides are perfect for duplex structures. They have very little effect on duplex structures. And because the temperature was at 125, if it had been at 500 degrees, then it wouldn't have been any good. Okay, but in this application, it was fantastic. And the result was that rather than buying all that nickel, they bought basically stainless steels. They saved over $8 million. So it's an excellent application that we've got. We do have a global oil major that's written a report specifically about welding, and they absolutely recommend basically over alloying. If they're welding duplex pipes predominantly, if they're welding duplex pipes, then they recommend welding with super duplex. So it's an over alloy. Okay, you're welding a 22 chrome with a 25 chrome over alloy. However, the interesting part was that for any super duplex welding that they have, they recommend using hyperduplex filler wires. So that's really good for us because hyperduplex is only available from ESAB. Nice application in Paris, the Louis Vuitton Museum. The use of duplex, 1,500 tons of duplex in there to support this structure. Used for several reasons. One is, again, because of the high strength, then you could reduce the weight. The high strength was sufficient to be able to carry all of this this structure. It's a stainless steel, it's a duplex, so it doesn't need any maintenance in terms of painting, for example. Fantastic. So that's a nice example. And then the last one that I have is a fairly recent one. This bridge was a rebuilt bridge up in the northwest of the UK. They used 450 tons of lean duplex in there, obviously welded it together with duplex. But as you see there, a quote from the architects: the duplex stainless steel was selected not just for durability and maintenance reasons, but also because its strength to weight ratio enabled a lighter structure that could be lifted into place as a single piece. In addition to that, they've got a bridge that needs no maintenance. They don't have to paint it. It's going to be very cost effective for years to come. That concludes everything that I wanted to say. I think my 30 minutes is just about up.